Hello everyone, it is with pleasure to give you this presentation together with my team on Team Cerberus, the technologies we developed, and how those allowed us to win in the DARPA Subterranean Challenge. The DARPA Subterranean Challenge represents the grueling effort for teams to develop technologies that will allow first responders and the industry to autonomously explore, characterize, and search diverse underground environments such as tunnel-like settings, for example, an underground mine, urban metropolitan infrastructure such as subway station, or natural cave networks that span across the world. To that end, our team aimed to develop a cooperative team of walking and flying robots that will be equipped with resilient localization and mapping in GPS-denied and perceptually graded environments, the ability for resilient autonomy to explore and search complex underground domains, the capability to operate in areas where there was no prior communications and therefore any communication networking had to be deployed by the robots, and of course the potential to perform equally well across complex and diverse underground environments. To that end, we assembled a team of experienced colleagues across the world for Team Cerberus. As was demonstrated by DARPA in the Subterranean Challenge, the interest is for a robotic solution that can navigate, explore, and search very diverse underground environments, from underground mines to a subway station to a natural cave and different types of caves across the world. Team Cerberus envisioned from the beginning a unified approach that will rely on legging and flying robots to autonomously explore and search such diverse settings. In this presentation, together with my colleagues, I'm going to present to you and we're going to show you how our team went about developing the versatile robots for subterranean environments, the resilient perception capabilities on board our systems, resilient autonomy functionalities, artifact detection pipeline, and our solution for communications. In further detail, we're going to discuss about dexterous and legged flying robot systems in Team Cerberus, the multi-modal sensor fusion approach for resilient localization and mapping across all the robots of Team Cerberus, a unified exploration path planning methodology across legged and flying robots, our high-performance artifact detection and localization pipeline, and also our solution for self-deployed subterranean communications and networking across our robots. And of course, I want to highlight that in this robot-oriented, robot-centric pipeline, the human aspect and the integration between human and robots persisted and remained particularly important.
Hi everyone. In this section, we will present the main mobility features of the robots of Team Cerberus. Specifically, we will talk about our legged, aerial, and ground platforms. So let's get started. The first robot we present is ANYmal C, the legged platform used by Team Cerberus during the final event of the DARPA Subterranean Challenge. ANYmal is a quadruped robot produced by ANYbotics and customized by the Robotics Systems Lab to create its Sub-T version. This version is equipped with multiple sensors including LiDARs, depth, color, mono, zoom, and thermal cameras. ANYmal has a total weight of roughly 55 kilos, a payload capability of 10 kilos, and an operation time of approximately 80 minutes when continuously walking. During the final event of the Sub-T Challenge, we deployed 4 ANYmals in the course, and we had them operating simultaneously. In the following part, we will see the main software components used for locomotion. The first module is a GPU-based terrain mapping software that is able to process input point clouds in real time and provide a terrain representation used for both locomotion and planning purposes. This video shows an example of the robot navigating in a narrow environment while the terrain representation is built during operation. The elevation map that you see is actually composed by multiple layers, each used for different applications. The elevation layer is mostly used for locomotion and visualization purposes, whereas the traversability layer is used to plan local traversable paths. Finally, the upper bound layer is used to handle negative obstacles during the local path planning phase. Another main software component is our deep reinforcement learning based locomotion controller. This video shows the perceptive controller used in different scenarios with ANYmal robot locomoting over a variety of rough terrains. This controller uses a policy trained in simulation and directly deployed on hardware, and it is also one of the main differences with respect to the other teams that deployed legged robots with a model-based locomotion controller. To achieve a high level of robustness, we also apply randomization during training. For instance, randomized height scans in the elevation map are applied to handle sensor degradation in extreme conditions and challenging environments. As you can see in this video, the robot is able to keep on walking even in an area where a lot of smoke was released. Moreover, mass, frictions and external disturbances are also randomized to be able to cope with slopes, stairs, and in general rough terrain. This policy was deployed on all the animals during the final event and proved to be extremely robust and never failed. The third component used for locomotion purposes is a reachability-based navigation planner, utilized to generate local traversable paths. This module is based on a reachability method which explicitly allows stepping over obstacles, and thus it is tailored for the animal quadruped robots. Specifically, giving a local terrain representation from the elevation map, the state of the robot and the goal to reach, the planner generates traversable trajectories. To do so, first the planner checks whether the torso, depicted in blue in the figures, is free of contact. This is done to avoid collisions. On top of that, the planner enforces foot reachability volumes, depicted in red, to be in contact. In this way, we ensure that the feet can reach the ground. Moreover, we provided the planner with template learning for steppable geometry to identify safe foothold locations. In addition, we deploy a local motion cost predictor that, given the high map and the current goal, provides estimated cost and risk, which then can be minimized during planning. This video shows ANYmal navigating different goal poses on uneven terrain. The planner copes with partial and missing map information and significant map noise caused by the onboard odometry system while maintaining fast update rates. The second robot we present is RMF, a resilient microflyer drone developed at the Autonomous Robots Lab. With only 38 centimeters in length and width and a total weight of 1.4 kilos, this is the smallest and lightest drone employed by Team Cerberus. This drone features a LiDAR and a camera sensor. Thanks to its agility, small size and robustness against collisions due to its custom frame, it can be deployed in particular confined environments. In this video, we can see RMF autonomously flying in a narrow section of the tunnel area during the post-event of the finals. The third platform we present is the Gaston Gagarin drone. This is also a collision-tolerant platform developed by Flyability and further customized by the Autonomous Robots Lab. This platform is specifically designed to cope with narrow environments and vertical shafts. This video shows the Gaston Gagarin drone autonomously flying downstairs through a narrow opening during the urban circuit, while being resistant against collisions during the autonomous descent. The fourth robot we present is the Alpha Charlie platform. This robot is based on a DJI frame and a customized flight control software developed at the Autonomous Robots Lab. It's a bigger drone compared to the previous platforms, but thanks to its higher payload capability, it can carry a broader variety of sensors, including LiDAR, color, and thermal cameras. Thanks to its multi-sensor suite, this platform can penetrate obscurant and dusty environments, also in the presence of smoke. The last flying platform we introduce is the Voliro Kolibri drone. This tricopter drone is produced by Voliro and further customized by the Autonomous Systems Lab. The tiltable rotor design makes the Kolibri able to change pitch independently of its motion, as well as hover at any given orientation. This platform has a considerable payload capacity and a higher operation time compared to the other drones of the team, and therefore it is specifically suited for long-term autonomy tasks in confined space, as well as vertical exploration tasks. The Armadillo Rover was the only wheeled robot deployed by Team Cerberus. It was used to support underground operations and extend communication range of the other robots. It is equipped with a high-gain directional antenna and connects to the ground station using a fiber optic cable that can be incrementally released using a spooling mechanism.
I am Shehryar Khattak, and on behalf of Team Cerberus, I'll be presenting an overview of the localization and mapping approaches deployed by Team Cerberus in the DARPA Subterranean challenge, and especially in the DARPA Subterranean final competition. Robot navigation in austere environments presenting a number of challenges, for example, darkness, fog, dust, narrow corridors were an essential part of the competition. And early on in the competition, we in Team Service identified that multimodal sensing would be a key element of our approach. Given this, we investigated a number of localization and mapping approaches utilizing different sensing, for example, LiDARs, thermal cameras, visual cameras, inertial units, and robot kinematics, and also understanding the synergy between these sensing inputs, that how we can use them in a complementary way so that robust localization and mapping can be enabled for robots in these austere environments. Furthermore, our goal was always to have an approach that was flexible enough to respect the different compute capabilities of each platform. So it was flexible enough that if we take out some of the components, it can still run on a compute limited platform. So for example, some of the platforms that are highlighted below show this point quite strongly. For example, on the left is our quadruped animal robot, and given its high payload capacity, it was able to carry a number of sensors, so multiple LiDARs, multiple cameras, thermal cameras, mono and RGB cameras, inertial measurement units. Furthermore, it had joint encoders, so also had more kinematic information. And also it had more compute capacity on board. But our flying robots, however, were limited in terms of the payload that it can carry. So for example, in the middle is our Charlie robot, which has a subset of all the sensing modalities that ANYmal carried. For it has a LiDAR, a thermal camera, an IMU, and a visible camera. However, it has an Intel NUC on board, so it's again much limited in its compute capability as compared to the ANYmal robot. And going further down the line, we have our Microfly robot, which was carrying an Austra LiDAR, an IMU, which is part of its autopilot, and a FLIR Blackfly RGB camera. And as this platform is quite limited in compute, it has a CADAS board on board, so it was only using LiDAR and IMU for its localization and mapping. So given these constraints and this diversity in compute and sensing modality, we opted to develop a flexible and hierarchical fusion approach. The flexible in the sense that given the subset of sensing modalities available, how you can utilize them, and also flexible in the sense that if the compute is limited, we can actually choose not to fuse some of the sensing modalities and still have a reliable or robust approach. And how we achieve this is by doing it in a hierarchical fashion, that you have your estimators running independently, and if their estimate is good enough, then that will come later on, it is propagated to the next step. And if it is not capable of running some module, you just ignore that one, and the pipeline again always goes from left to right. And this approach we term it as complementary SLAM, because which enables to take advantage of all the complementary capabilities of all these sensing modalities that they can provide. For example, thermal cameras are very good when navigating through fog, and LiDARs are very good at creating large-scale maps or providing direct measurements. And again, as mentioned, for propagating these estimates from left to right, each step was checked given some health evaluation criteria. So these criteria were both at the data level. So for example, for camera images, we would be tracking spatial entropy not only in the spatial sense on the image, but also in the temporal sense, to understand if there are some features that are untrackable. For example, if you have certain dust and you are tracking spatial entropy in a temporal manner, you can actually remove dust from the images and still track features that are more stable and still do VIO in a industrial environment. And then we also had estimation level metrics. That, for example, if you are registering two point clouds, what is the registration score, or what is the minimum eigenvalue of a Hessian matrix that can make you understand that how good this estimation worked. And we used a combination of both these health evaluation metrics at each level, and once the estimate passes this, and only then it is propagated or fused into the next level. And the idea was that you always have a estimate of robot, and you always have a map that keeps propagating no matter what environment you're traversing. And this was our onboard estimation approach. Given this, it was deployed on all the robots that were actually made into the competition circuit. So for quadruped animal robots, so Chimera, Cerberus, Camel, and Cayman, the individual distances of each one is also listed under their name in their respective colors. And what we show here is the map created by each robot in different subsets of the environment which it was allocated to explore autonomously. And in total, we traversed a total of 1.7 kilometers in all these diverse environments, and they were able to map it. All these estimation approaches were running in real time on board the robot. However, this was one part of our strategy, and these maps were then merged into a centralized global map that was available for the base station and the human supervisor. And it was each robot's onboard map, along with some of the sensing data, either processed, for example, features from visual images, or some raw data, for example, in terms of point clouds, being sent back to the centralized server. And the server did, it tried to find multimodal constraints not only for that individual robot, but also among robots, so that it can create dense constraints and then create a nice global map by merging all the information that was coming from individual robots. And in the final run, this is the final map of all the 4 robots merged on top of each other. The artifacts reported were a combination of both onboard and the global solutions. The global mapping given the amount of data and constrained by time. For example, if an agent comes very late and provides a huge amount of data, then you're again limited by the time that how much optimization you can do while merging this map. So in the final run, we used a combination of both onboard and global solutions, and this is the final map. And I would be happy to answer any questions that you have about these approaches in the Q&A.
Hi everyone. In this section, we will present the main autonomy features of Team Cerberus. The development of the Cerberus autonomy is driven by the challenges of the subterranean environments. We aim to enable resilient autonomy with minimal human supervision in very large-scale environments that present challenges such as difficult terrain, narrow passages, and multi-branching and multi-level topologies. The autonomy system should be generalized across all the robots, but at the same time capable of handling robot-specific constraints and exploiting the advantages of robots' mobility. The human supervisor is responsible for high-level coordination, deciding what part of the environment each robot will explore, while each robot performs its assigned exploration task fully autonomously. We utilize a graph-based exploration planner that is developed to work across all the robotic platforms of the team. This planner has a bifurcated local and global planning architecture to handle large-scale environments as well as perform efficient local exploration considering robot constraints. The paths provided by the high-level exploration planner are then tracked by the robot-specific navigation modules. At the core of our autonomy lies the graph-based exploration planner called GB Planner, which utilizes a bifurcated local and global planning architecture. The local planner is responsible for rapid exploration within a local space around the robot and provides functionalities to handle robot-specific constraints. On the other hand, the global planner is responsible for repositioning the robot to unexplored areas of the map when the local layer cannot find an informative path. At the same time, the global layer also provides safe paths to return the robot to the home location within the robot's endurance or a predefined mission time. In the first step of the local exploration planner, a collision-free graph is built within a volume around the robot. This volume is adaptively calculated according to the local environment geometry. In case of aerial robots, the edges of this graph are simply collision-free straight lines. However, for legged robots, we also check the existence of a supporting ground below each edge and vertex. To check this, each vertex is projected downwards on the volumetric map to check for the existence of an occupied voxel below it. Due to possible gaps on the ground in the volumetric map, which can be caused by low LiDAR incidence angles or water on the ground, we also check a few other points around the vertex to verify the existence of ground. Similarly, each edge is interpolated and projected to check for supporting ground. Along with the existence of the ground, each projected edge segment needs to have its inclination within a feasible limit. Finally, some vertices which are in free space but do not have a supporting ground are retained in the graph as hanging vertices if they can be connected using edges having feasible inclination. These vertices are used for information gain evaluation, but the edges connecting to them are not commanded to the robot. In the next step, we compute a volumetric gain for each vertex in the graph that relates to the amount of unknown volume the robot will map if it would have been at that vertex. Then, we extract the shortest paths in this graph starting from the current robot location. For each path, the volumetric gain of its vertices is aggregated and the total information gain, called the exploration gain, is calculated as shown in the equation here. As this is one of the most computationally demanding process, two modifications are done to reduce the computational cost. First is to calculate the volumetric gain only at the leaf vertices of the shortest paths, and second is to cluster the leaf vertices to approximate the gain of all the vertices in the cluster by one vertex. Finally, the path having the highest exploration gain is selected. This path is further improved for safety to be away from the obstacles and then commanded to the robot. We will now explain the global planning layer of GP Planner. The global planner maintains a lightweight global graph built by adding high exploration gain paths from the local planning step and identifies high volumetric gain vertices in this graph called frontiers. When the local planner cannot find an informative path, the robot is repositioned to one of these frontiers to continue the exploration. Additionally, the global planner provides a safe path to return the robot to the home location within the robot's endurance or a mission time limit. Here, we summarize the autonomy stack of each category of the robots. The aerial robots have a relatively simple architecture, with GP Planner being the main autonomy module. The ANYmal uses a behavior tree to coordinate various functionalities of the robot. These include autonomous exploration, inspection of specific areas using the pan-tilt head, and handling the commands given by the human operator. If the robot loses communication with the ground station, it is allowed to explore independently for a given time, after which it queries GP Planner for a path to return to home or previous communication point. In case any of the high-level autonomy modules fail, and the robot is idle for more than a threshold time, the behavior tree triggers a recovery behavior in which the robot backtracks its path to the home location or previous communication point. Any paths given to the robot, be it by GP Planner or manual waypoints by the operator, are sent to the navigation planner to track. The navigation planner is allowed to modify the commanded path locally to maximize safety and enable efficient locomotion. In this video, we show two experiments conducted as part of the preparations for the final event. The experiments were conducted in the Hagerbach mine in Switzerland. The first part shows a mission conducted by the ANYmal. This demonstrates the ability of the planner to navigate over slopes, handling multiple branches, and autonomous homing. At this point, the robot reaches a dead end, and the global repositioning is triggered. Towards the end of the mission, autonomous homing is triggered, and the robot returns to the home location. The second part is a mission of the RMF-Obelix collision-tolerant robot. This shows the planner running on a computationally constrained system. This mission involved fully autonomous exploration followed by homing, totaling an 8-minute long mission. Here, we show an instance in the prize run where the animal is exploring the tunnel section and then enters the cave section, passing through some confined areas. The path given by GB Planner is shown in yellow, and the path shown on the ground is the traversable path generated by the navigation planner. At this point, we can also see the planner planning over a very steep narrow slope in the cave section. Finally, this figure shows the combined map of the prize run along with the paths of all four animals.
Hello everyone. In this section, we will present the object detection pipeline of Team Cerberus. We detail the process for training the object detection algorithm, estimating the location of the object once detected, and reporting the artifact to DARPA. The hardware present on each robot for this purpose is also described, followed by the results from the prize round of the final event. The object detection algorithm is based on YOLO v3. A large dataset was collected for training the neural network with an aggregate of over 40,000 labels. The network was trained for up to 16,000 iterations with a batch size of 16 and a mini batch size of 4 images. The same set of trained weights were deployed across all the robots of Team Cerberus. To make detections more robust, a variety of camera sensors having lenses with different field of views were used to collect images. A combination of high and low resolution images with different zoom levels were collected against different backgrounds using the robot's onboard cameras and specialized inspection payload. To increase the detector performance against difficult settings, specific attention was paid to the collection of data. A large number of images were collected in tunnel, urban, and cave-like environments with varying light conditions. Potential issues with detection were identified and specific data was collected to prevent them. Images containing motion blur, obscurants, and with artifacts against particularly challenging backgrounds were collected. In this slide, you can see the top images containing the fire extinguisher and the backpack against a red background, while the lower images show the vent against a white background, which were found to be particularly difficult to detect. The next images show some instances of collected data with motion blur and obscurants. Once the detector identifies an artifact in an image, the location estimation is performed on board each robot. For visually detected artifacts, the bounding box is divided into pixels and rays are cast in the robot's map for each pixel using the camera parameters. A sphere is constructed in the map and centered at a median point of intersection of the rays. As the robot moves in the environment, the object is seen from multiple angles and the same process is repeated for every detection. As new measurements are received, the center of the sphere is updated to be the mean of the estimated position of the artifact. Probabilities for the presence of each artifact are updated with every detection, and this process stops when a threshold is reached for any artifact class. The artifact location is then sent to the human supervisor. For the phone, sub-T-cube, and carbon dioxide gas artifacts, we use Bluetooth and CO2 sensors to measure the signal strength and gas concentrations respectively. The measurements from the sensors are recorded over a fixed time window. The locations of the robot corresponding to detections exceeding a minimum threshold are stored. When the detections drop below the threshold as the robot moves away from the artifact, the weighted mean of the robot positions corresponding to the top measurements is calculated. This mean position is sent to the human supervisor as the location of the artifact. Once the artifacts are detected by the robots, they are sent to the ground station. The human supervisor at the ground station is presented with the image of the detected artifact. The estimated position can be visualized on the map using the UI panel on the right and then reported to the DARPA server by clicking on the artifact in the map. The human supervisor is also presented with an option to report the location of the artifact based on the robot's estimation or to report the location as optimized by the multi-robot mapping framework. To detect the artifacts,
Each robot had a different set of sensors and hardware for processing the images. ANYmal C was equipped with a Jetson Xavier GPU that performed detections on multiple image streams. Cameras on the AlphaSense payload and a higher resolution zoom camera on the inspection payload were used to detect the artifacts. The aerial robots used lightweight hardware for performing object detection, with the M100 Aerial Scouts and Kolibri platform using the Intel Movidia stick and the RMF-Oblix platform using a neural processing unit. The Super Megawatt platform used a dedicated GPU on the onboard computer. For the prize round of the final event, we correctly detected a total of 23 artifacts. The reported location of each artifact is shown with the color of the robot that detected it.
Hi everyone and welcome to the communication block. In this short talk, I'm going to cover the networking structure used by Cerberus in the final run of the competition. Furthermore, I will talk about systems that had special networking capabilities as well as the software that was running to enable communication. In complex and large-scale environments, such as faced during the Subt challenge, a single communication point where all the robots connect to directly was not sufficient as the topology would not allow to maintain communication. For instance, the signal strength drops drastically with distance in such environments. This becomes obvious if we look at the topology of the Nyers mine, where a signal loss can happen already after a single turn. To keep the exploration going continuously, we focused on pushing autonomy of the robots. But at the same time, communication is the core component to provide situational awareness to the operator. So the longer the communication is established, the longer information can be transmitted to the operator. And earlier, the data can be sent again once the robots return. To establish communication for as many minutes as possible during the run, Cerberus used portable wireless mesh network nodes manufactured by Regent. These nodes had a dual capability in the sense of forming the actual mesh network, as well as providing an access point for clients that were not directly extending the mesh network. So let's get started with the networking structure. From mission control, we connected the first mesh node with an Ethernet cable. This node was directly mounted on a tripod in the staging area of the competition and served as a base station. Moreover, we connected an optical fiber cable to a movable Rover. This way, we could extend the range of the high bandwidth connection to the base station. Each one of our legged robots was carrying a Wi-Fi node and therefore is part of the mesh network. On top of that, 2 of the 4-legged robots also had the capability to deploy up to 4 mesh nodes to extend communication even further. The aerial robots did not directly extend the mesh network, but connected to the access point broadcasted by each mesh node. As all nodes were broadcasting the same access point, the aerial vehicles could change which node they used to connect to the base station via the mesh network. This also included the walking robots. This concludes the networking structure of Team Cerberus. I'm now going to talk in a bit more detail about the Rover and the legged robots. Our tethered Rover was carrying an optical fiber cable reel that could be used to spool and unspool the cable while driving. The cable had a length of 1000 feet. We mounted a directional panel antenna on the Rover to extend the Wi-Fi range. As highlighted in the previous overview, this robot was part of the mesh network. 2 walking robots were carrying droppable nodes that could be deployed one by performing a tilting maneuver while releasing the magnet that is holding the Wi-Fi beacon. The beacon's antenna holder is 3D printed and had a passive release mechanism to unfold as soon as it was deployed. Let's move on to the software packages used by Cerberus to establish communication during the challenge. we deduced the following requirements. The software was required to handle a multi-agent system as well as unreliability and connection losses. A scalable solution would also use low bandwidth. As a team, we decided to stick to ROS1 for this competition. These requirements are not fulfilled by the standard implementation of communication in ROS1. Therefore, we had to evaluate additional solutions. Specifically, we looked into Multi-Master FKI and the Nimbro network. We decided to use Nimbro network for the following reasons. First, it can handle a multi-agent setup in the form of a multi-master operation. This also applies to the Multi-Master FKI solution. In terms of reliability and handling of connection losses, the Multi-Master has an advantage that it can do automatic topic and host discovery. However, we did not really need that, as it was clear from the beginning which information had to be sent. What seems like a drawback of Nimbro in the end was more of a benefit, as we could clearly specify which topics we wanted to transfer. Nimbro also has forward error correction implemented in contrast to the Multi-Master FKI. The functionality to limit the rate of topics as well as the built-in compression also gave us the opportunity to reduce the consumed bandwidth. And the implementation of Nimbro is in ROS1. The multi-master setup of Nimbro meant that we run a ROS core per agent as well as one ROS core on the base station. Each agent then runs a set of receiver and sender nodes. These nodes then directly communicate with each other over TCP or UDP, where we could select which topics and services we want to exchange. Another functionality that we implemented in the scope of the competition was the so-called topic on demand. Let's assume you are running a sensor or processing node that provides information at a given frequency. While the onboard processing might require this specific frequency, the operator is probably not interested in receiving information at that frequency, but rather at a specific point in time. An example could be LiDAR data of a sensor or a map of the surrounding terrain. Instead of just throttling the output to a fixed rate and streaming the throttled topic, we put an additional module in between. Upon request of the operator, an on-demand node would forward this request to the robot via Nimbro. The corresponding node on the robot then collects one single message and sends it over Nimbro to the requesting node on mission control. This allowed us to get data only at that time point when the operator needed it.
Great. With my colleagues now having presented all the details for each of our main functionality modules, from robots to perception to autonomy, artifacts and communications, I would also now like to discuss how we competed in the competition in the Subterranean Challenge from 2018 to 2021, and also some lessons learned throughout this fantastic experience. In the Tunnels record, in the first official competition event of the Subterranean Challenge, our team did not participate with extreme capability to score high. Quite on the contrary, we faced problems with our deployment of our legged robots. Our flying systems performed autonomous exploration reliably, but we did not score a point with them. And eventually we scored most of our points with a wheeled robot we had with us, which was strategy-wise repurposed to undertake the major exploration and artifact scoring responsibility. As you can see, with our map on top of the ground map from DARPA, we explored a very little part of the environment, and even though this was a small part, we already had some significant drift. In the urban circuit, the second competition event, we had already much more mature robotic systems, both legged and flying. Our legged robots were able to operate throughout the deployment of a mission. We were not able to traverse reliably stairs and other such complex locomotion challenges. However, we were able to score sufficiently high, purely relying on our core robots, legged and flying, and our roving robot was only used for the purposes of communications extension. It has an optical fiber cable, it's connected to the ground station, and a high gain antenna. And it was already the first time that the artifact detection pipeline, although not very mature, allowed to detect a significant subset of the artifacts automatically. This is what we achieved back then in the alpha and the beta course of the urban circuit of the Subt challenge. In the final event, our team came much more prepared with much more capacity in terms of the robotic systems utilized. We already had switched from the ANYmal robot to the ANYmal C robot with, I would say, an order of magnitude improvements in locomotion capabilities and robustness and system reliability. Our perception system remained focused on its capacity to enable resilient localization mapping in GNSS GPS denied environments that presented sensor degradation, including smoke and other types of obscurance. Much more field tested and verified and robust unified exploration path planning across legged and flying robots. Mature artifact detection and localization pipeline, both vision-based and also based on Bluetooth and gas detection. Relatively more mature communications and networking solutions compared at least to our previous deployments. And as we participated in the final event, we quickly identified that our legged robots were the best fit for the task, as the environments were, for a large subset, particularly confined. And with each robot being able to explore automatically on its own, autonomously on its own, and as long as we provide an allotment of an area, the robot will explore and make sure to come back into an area with communications link available. We went for a technique that will allow us to explore to span the exploration with as much breadth as possible early on in the prize run of the Subt challenge, and then progress incrementally deeper into the underground environment, while simultaneously, of course, detecting and scoring the artifacts. Given the above, this video presents instances of our participation in the prize run, which essentially allowed us to win the DARPA Subterranean Challenge finals. You see our main exploring robots, 4 ANYmal systems, so-called CERBERUS, Chimera, Camel, and Cayman, exploring different areas of the subterranean environment that DARPA had created. 2 of them, CERBERUS and Chimera, incorporate this sensing turret that you just saw that provides more cameras to detect artifacts, whereas the other 2, Camel and Cayman, are allowed to carry communication breadcrumbs to further facilitate the communication network underground. Our human supervisor was giving areas to be explored by each robot and an allotment of time for each of these explorations, and the robot will make sure by the end of this time allotment to be back in communication link. Without showing all the video, this is how we explored a significant part of the subterranean environment of the competition, managed to detect and correctly report 23 artifacts, and this gave us the final win. This is our team, and that we were able to be there in Kentucky for the competition. Of course, many more people were behind the scenes to support the technology of these systems. This is also all the robots we brought for the final event. This is some instance of us winning the competition and holding the prize, of course. And with that, I want to go into the lessons learned. So I want to highlight that from our perspective, it was quite important to invest from the beginning into one solution, this combination of legged and flying robots, and also unify a lot of the technologies for perception and path planning early on. Despite the fact that this meant for us that not everything was very mature in the beginning, we believe it was a successful direction, and we also saw from the other teams that a lot of the other competitors eventually utilized significantly legged and flying robots in their competitive rounds. We believe it's also very important to focus on perception autonomy, and robust performance across those allow to offset and mitigate the risks from other tasks, for example, from not having the most robust communications. Focusing on system reliability and readiness for the competition is important, but of course, again, one has to develop novel technologies, and this is what the Subt challenge called for. So we need a good balance between developing good novel technologies, but also freezing working software well in advance of the competition and making sure that things are ready to be deployed for the event. I think having a robust communication networking solution remains important, but luckily limitations in communications performance were able to be mitigated, as mentioned, with higher degrees of autonomy. And I think it's also very important to know the capabilities and the limitations of every platform you bring. One needs to bring diverse robotic systems in a team, and a collaborative team of systems to explore complex underground environments. And it's very important that the humans that make the decisions deploy the best robot for each task. With that, I want to close by outlining our core publications. The majority of our work is published, and people can see what eventually we did, both in terms of the perception pipeline and in SLAM and volumetric mapping, etc., etc., terrain mapping, multi-robot mapping, artifact detection, etc., etc. our path planning software for exploration, and also the path planning navigation software for ANYmal to account for complex terrain. Our systems paper for the phase 1 and phase 2, so the tunnel circuit and the airplane circuit of the competition. And of course, we want to highlight that we do try to open source significant components of our work to the benefit of the community. We here provide links to some of these repositories, but also our organization GitHub links where more work can be found. With that, I want to thank you. I want to thank DARPA and everyone that participated in envisioning and facilitating this competition. Of course, all the competing teams with which we competed in the score, but there was a sense of collegiality and partnership throughout the 3 years of the competition. All the community, of course, in robotics that pushed the frontier for us to be able to sit on top of significant contributions. And of course, with that, I want to spend a second to thank my team, Team Cerberus, and all the members that throughout 3 years contribute to our technological capabilities and to our success. Thank you.